Hydrogen often gets talked about as a future energy solution, but hydrogen has been utilised for years. The importance is making it clean, with endless applications beyond traditional uses. But behind every hydrogen technology, whether it's fuel cells, industry processes, or transport systems, there is a huge amount of science making it possible. Hydrogen is a powerful energy carrier, but also difficult to produce, store, and transport efficiently. That's where material science becomes critical. Researchers around the world are exploring how advanced materials could help store hydrogen more safely and more compactly and more economically, unlocking new possibilities for its use in transport, industry, and energy systems. Today I'm joined by Professor Tim Mays, Emeritus Professor at the University of Bath, whose research has helped shape global understanding of the hydrogen and its uses. We'll explore how this field has evolved, what breakthrough scientists are working towards, and how fundamental research connects to the real-world deployment of hydrogen technologies. Thank you for joining me today, Tim.
It's great to be here, Karen. Thank you.
Brilliant. So what first sparked your interest in materials chemistry and energy research?
Well, it's going back into the last century, last millennium, when I did my PhD. I won't tell you when. It'll show how old I am. I did my PhD on materials used in nuclear reactors. And I had great fun. I enjoyed being a student, perhaps too much. But what it did do, it turned me on to how materials can help improve energy conversion, energy generation, and in this case in nuclear reactors. So I spent 3 years studying that and enjoyed every minute.
Brilliant. And so hydrogen storage has been a focus of your work for many years. How did you first get involved in hydrogen?
Like all these things, it's sort of by accident. After I finished my PhD, I did some contract work called postdoc work on different materials used in different energy systems. And one of the problems I was working on, it was a mathematical problem, but it involved understanding how materials behave in energy systems. And my old PhD supervisor and later postdoc supervisor came into me one day and said, you know the work you did on your PhD? And I sort of said, yeah. And he said, well, that could be turned to look at a slightly different system. And I thought, okay, that sounds interesting. And the system was what's called adsorption. And that what adsorption means is when a gas comes along and sticks on the surface of a solid. Can you imagine like Velcro?
Oh, okay, yeah. I do understand that, yeah.
Yes. Well, that's as good an analogy as any,
no, I
think.
like that analogy.
And the model I had in my PhD was applicable to this different system, this adsorption system, Velcro system. And the first problem I dealt with was storing methane, natural gas. And this was for a particular kind of energy system using natural gas. But
when you say natural gas, that's what we use in our homes today?
Natural gas is exactly what most of us use in our homes for heating, and actually what's mostly used to generate electricity in power stations, actually, now that coal has more or less disappeared. And so the model I had in my PhD was applicable to natural gas storage. And then it seemed like a natural progression to go on to hydrogen. If I may tell a little story about how that developed.
Yeah.
The EPSRC, the Engineering and Physical Science Research Council, opened a competition to develop a new consortium for hydrogen. And they invited a lot of people along to the Royal Institute of Chartered Surveyors in London for some reason. And we all went along. There were the great and the good, me included. I was only quite young at the time. And they were trying to establish a group of people to start a consortium to work on hydrogen. And you got these people walking around with clipboards, sort of looking at people having a chat and stuff like this. And we didn't quite suss what was going on, other than they were assessing whether or not we were the right stuff, like astronauts, but working in this area. Anyway, a few weeks later, I was in Japan, as it happened, and for a conference. And they rang me up and said, we'd like you to lead a consortium. on hydrogen. And I was quite young, and I think they felt that I was sort of gung-ho, and I suppose I was. But they want me to work with a guy who was Professor of Chemistry at Oxford. And so the two of us together, a relatively new early career academic like I was, and this guy at Oxford who was obviously very senior, we worked together for the first large consortium. This was 2003.
Mm-hmm.
And really from that, my interest and career in hydrogen really developed. So we worked for, I don't know how many years it was, 8 or 9 years on this consortium. And it was a consortium with lots of people in different areas. So it wasn't just storage, it was production of hydrogen, storing it, moving it around, using it.
Mm-hmm.
And I had a lovely time. I enjoyed myself. I enjoyed the power of being the principal investigator. And that really helped my career development. So it was almost not quite by accident, but it was, these things are never linear. They never follow a straight line. And I was just, I guess, lucky.
Yeah, but so when you first started doing that in 2003, were you looking at green hydrogen, or were you looking at just better production of hydrogen?
It was everything. It was making more of it, making it greener, which means using or emitting less carbon dioxide. It was making use of it to harvest the energy back out again in a fuel cell or combustion. And actually, it was a complete change in direction. Hydrogen is traditionally used in things like oil refining and making ammonia that goes on to make fertilizer. It wasn't really seen as a very interesting material or substance to use in energy systems. But because people recognised that climate change was taking over and that resources were in fossil fuel in particular were declining, they're thinking, well, let's open our doors a little bit to new ideas, and hydrogen became this potential medium to help us move away from fossil fuels. Incidentally, I prefer the word defossilization rather than decarbonisation because it's getting rid of oil, gas and coal.
Mm-hmm.
And so we were really innovators in how to, one, run a big consortium, and two, work out how that can really make an impact on technology to help, whether it's green hydrogen, making green hydrogen, low carbon hydrogen, storing it, which is my area, and then using it. So it ran for a number of years. It wasn't always smooth running, I must say. Sometimes the challenges we were facing proved to be so tough and difficult.
Mm-hmm.
But what happened was that started a journey that's now ended up, if I may say, with the projects I was working on until recently, over 23 years or so.
And what do you think was the impact from that particular consortium that you were working on?
I think there were two. One is how to run a consortium, which is not easy, especially when you have...
Quite early on in those consortiums in those days?
They have been running, but I think that hydrogen's got a multifaceted thing. It's got lots of things going on with it. And so whether it's production, storage and use. And so it was not only the size of the consortium, it was also the fact that it was people working on lots of different things and they had to be stitched together. So the first thing is how do these consortia run effectively to deliver interesting and useful new knowledge and understanding and impact. And secondly, there were some genuine innovations on the production side, particularly at St Andrews with Professor John Irvine, one of the world's leading physical chemists. And there were lots of interest in enhancing fuel cells, and there were significant developments, even if I say so myself, on storage, particularly in solid-state storage, in materials.
Hydrogen is described as difficult to store. You mentioned some work that you'd done there. Why is that? What makes it so challenging with hydrogen?
Okay, well, there are two aspects to this. One is that hydrogen has more energy per unit mass, in other words, per kilogram, than any chemical fuel, gasoline, diesel, kerosene, you name it, 3 times as much. So, in other words, for the same amount of energy, you only need a third of the amount of hydrogen than you do of natural gas or coal or any of these
or electricity.
Electricity. No, let's move. Let's not make life more difficult by thinking of electricity. Okay. These are chemical fuels used, like natural gas and derivatives of oil, like kerosene and gasoline. So on a per mass basis, it's brilliant. but it's low density. What that means is the volume that this occupies is enormous. So let's give an example. If I wanted to drive a car, say 300 miles, I'd need about 5 kilograms of hydrogen compared to 15 kilograms of gasoline. However, it would occupy a volume as big as the car, bigger than the car, without doing anything to it. So in other words, you have to
have a little trailer going along at the back.
You could do. You may laugh, but people did think of not doing anything to the hydrogen, just having it in a big balloon behind you, but that's not really practical.
No.
So the whole storage problem is, how do I get a lot of hydrogen into as small a space as possible?
What have you done to solve that challenge?
Well,
which is
I wouldn't claim that I've solved them, but I've been involved in people who have. And the first one is to compress it. Simply put it in a bucket and squash it. And you can do that, and it increases the density. But it takes a lot of work to do that. A lot of energy you have to put in to squash it. And that energy takes away from the energy you want to get back out of it later on. So in other words, it seems not really efficient in that sense. It means you just don't recover all the energy you put in. So you can squash it, but you run out of steam in squashing it when you get to about, I'll go technical for a minute, 700 bar. 700 atmospheres. Yeah. So that's 350 times the pressure in your car tire. You run out of steam. It doesn't. You can't compress it much more after that. It doesn't work. But it does produce very high density hydrogen, which is good. But you do have to put this lot of energy in. The second one, which is quite even trickier, is liquefying it. And to liquefy it, you need to go to temperatures that minus 253 degrees Celsius.
That sounds a bit nippy.
It's pretty chilly. For example, liquid nitrogen is minus 200 degrees Celsius. So it's 50 degrees lower than liquid nitrogen or liquid air. So to liquefy it, which does really produce nice high-density hydrogen, you need to put a lot of energy into liquefy it. So in the same way as compressing it, you need to put energy in. You need to put a lot of energy in to liquefy it. And not only that, but you need to keep it there. You don't want it to boil off. So you need to put a lot of energy into the materials that contain liquid hydrogen. And of course, you need to make it safe so it doesn't leak. Mm-hmm. So all this investment means that, yes, you get a lot of energy from the hydrogen, but you've put a lot of energy into the containment and getting it there. Yeah. So liquid hydrogen, high pressure hydrogen. The sexy way, is to try and engineer a system that's midway between this high pressure and the low temperature. Right. Because that means you don't have to put so much investment into the materials that contain it or to the processes that get you there. And one way of doing this is, which really I picked up from the work that I did on natural gas, is that there are materials that contain little pores, holes in them. And typically these pores are a millionth of a millimetre. They're literally only a few atoms in diameter. So they've got little holes in them, these porosity. And it turns out that any gas, whether it's natural gas, whether it's oxygen, nitrogen, hydrogen, inside these little pores, it's unbelievable when you think about it. These pores act like a compressor. They squash. Ah. And what happens is the hydrogen densifies, so it's rather like a little nano compressor. Ah. And so in these pores that are a millionth of a millimetre across, it's very difficult to visualise them. Mm-hmm. They act as these compressors. So if you can get the hydrogen in there via this process called adsorption, where the gas sticks to the surface.
Ah, yes, like the Velcro.
So the gas is stuck to the surface like Velcro, and they're inside these little pores, and these pores squash it down. That's what I've been working on for, and both the theory and the practice of how that will work at higher temperatures than liquid hydrogen and lower pressures than high pressure gas. Mm-hmm. And the other aspect of this, it's very easy to get it back out. All you need to do is warm it up a bit. It does still have to be cold. At the moment, it still has to be cold. But all you need to do is...
Same temperatures you were talking about?
No. I mentioned liquid nitrogen before. Unfortunately, it still has to be at those kinds of temperatures, about minus 200 degrees Celsius. But that's a lot less energy intensive than minus 250 degrees Celsius.
Yeah.
So we're moving in the right direction.
Yeah.
And also it can work at pressures maybe 30 or 40, 50 atmospheres, which is way less than 700 atmospheres, which you need for high pressure gas. So we're moving in the right direction on both counts. Higher temperatures, lower pressures. Plus, you need to engineer the materials to have there's a sweet spot with the pore size. And we still don't know why that is. I have an idea, but no one believes me. Is that there's a sweet spot where you get the maximum density. A little bit bigger, the effect of the pore wall doesn't have an effect. And a little bit smaller, the hydrogen can't get in. So there's like a little sweet spot.
Because hydrogen molecules are very small.
It is very small, but it could mean that the pore width is so small that hydrogen finds it very tricky to get in.
Yeah.
Especially when the temperature's low.
Yeah.
It's not a simple issue of how it fits. It's how it gets in there in terms of the rate at which it gets in there. It could take forever to get in there.
Right.
So this sweet spot, and I won't bore you to details, but it's 0.7 nanometers, 0.7 millionth of a meter, and that seems to be a sweet spot. The process is this, and maybe it's helped to think we make the hydrogen by using renewable electricity to split water, H2O, into hydrogen and oxygen. The hydrogen, so the electricity is the energy in bit. The hydrogen then, we say, well, what do we do with it? I know, why don't we put it into a spent gas field or an underground salt cavern? And we can put the lid on, and when we need energy back again, we open the lid and off hydrogen comes, and then we can harvest the energy by burning it or putting it through a thing called a fuel cell. And in the current world where there's geopolitical uncertainty every day of the week, it seems to me, this idea may be very, very attractive, because what it'll do, it'll remove the necessity of buying electricity or buying fuel from Europe or further afield. So this energy security aspect from hydrogen is very interesting. And it's energy storage. Use the renewable electricity. And some people will say, well, why don't we just use the electricity that's generated from a wind?
Yeah, absolutely.
Well, the thing is, renewable electricity is intermittent. Solar, for example, day and night. Wind is unpredictable up to a point. And what happens is that demand for electricity doesn't always match when you're making it.
Right, yeah.
And what you want to do is, when there's more electricity than you need, why not use that excess, as it's called, to split water? That generates the hydrogen and oxygen. You then put the hydrogen away in a salt cavern, or it could be into some of the systems that I've been mentioning, high pressure gas, liquid, or solid state, and then recover the hydrogen later on when you need it. It could be seasonal, winter to summer, or the other way, it'll be summer to winter, because you have a lot of sunlight from solar PV, photovoltaic. And so hydrogen has and that was the real original reason why people were interested in hydrogen, as a way of storing excess renewable electricity.
So obviously we've talked a lot, Tim, about storage of hydrogen. What are some of the other challenges that research is looking at to ensure that hydrogen can be used in, we talked about smoothing out the patterns of the usage of electricity in the grid, many other applications, which I'm sure we'll touch on. But what are the other things that you need to solve for us to really be using hydrogen in our energy system?
It's a good question. I think of what's called the value chain. You start with making it, you then move on to storing it and moving it around, and then you use it. And that's called the value chain. And each of them have difficult technical challenges. We've mentioned storage. Now, making it is not just a case of putting electricity into water and off comes hydrogen. I mean, that's what happens, but you need to do it effectively. And that's not always straightforward. So the materials that are used in what I call electrolyzers, using electricity to split water, they need to be more efficient, they need to be lower cost, and they need to be made so you don't have to rely on very rare elements and metals to run them. So there's a lot of interest in developing low-cost, efficient electrolyzers to make what's called green hydrogen. Green because it's made from renewable electricity.
Yeah.
So it's all very low carbon. So production, you can also make hydrogen from heat, and people are thinking of the high temperatures in future nuclear reactors. The UK is now committed to having a next generation of nuclear electricity that can be used to, the high temperatures inside the reactors can be used to generate hydrogen by essentially breaking down water, hydrogen and oxygen. And in fact, the hub that I was involved in before I retired had a meeting recently with the nuclear industry in order to try and explore what needs to be done for future nuclear reactors.
So would that be that hydrogen then would be used as the energy source for the nuclear reactor?
Not really. It doesn't.
It's a byproduct.
It doesn't imply that the hydrogen will be used in a nuclear application. All you're doing is generating a fuel that can be used in all sorts of ways.
Okay, so it would then be able to go on and be used.
You could use it to store electricity in the same ways that we mentioned before, but we can go on in a minute to talk about other things that you can do with hydrogen. So the production side is very important. The end use is also, what are you going to do with it?
Yeah, absolutely. And we've been exploring some of that in these podcast episodes. Yeah,
absolutely. And there's one of the biggest problems with hydrogen is to people want to make it and people want to use it, but they're not always matched up. And to make an economy work, you need to match up. People want to make hydrogen, they want to know they can sell it to a user. And a user wants to know that they can develop their use systems with lots of available hydrogen, and that's not always matched up.
At a price that they...
Economy will drive it, you're quite right. Anyway, so the end use. Now, the end use I've mentioned to you before, you can harvest the energy back from hydrogen using either combustion, you can burn it in the same way as you burn natural gas, and that could be used for heating in buildings and people's homes. You can use it to generate electricity in a big gas turbine, in the same way as natural gas is used now. You can also use hydrogen, for example, in the ceramics industry for glass and glasses and ceramics. And you may know that these involve very high temperature burners. Now, traditionally, they use natural gas or propane, another form of hydrocarbon. You can use hydrogen. Especially as the product doesn't. The thing about combustion or any way of harvesting hydrogen, there's no carbon there. There's no carbon. So the beauty of this is that you can burn it, but you don't produce carbon dioxide. So hydrogen has this sort of multifaceted side to it. It can be used in, you mentioned iron, ceramic manufacture, heating, chemicals, particular ammonia, but other ones. And so in other words, we're cutting the cord with fossil fuels. We don't need natural gas. We don't need coal. We don't need oil. Hydrogen can do the job, but you've got to make it. And I mentioned to you before, without making it effectively or efficiently, then you're in a difficult position. You've got to move it around, and finally you can then direct it towards whatever you want to use it for. Whether it's rainy day storage or seasonal storage, as I mentioned, but it could be into these other industries. And that's the beauty of hydrogen, its flexibility and its adaptability. And you mentioned transport. That's a big potential use. We've all driven around recently in cars with diesel or gasoline. You can do that with hydrogen. So hydrogen is perfectly engineered to in a car for you to drive around in, and it doesn't produce any carbon dioxide. It only produces water at the tailpipe.
You mentioned that it would need to be very big.
The storage is probably the most difficult bit, because you don't want a car that's dominated by the store.
No.
And in fact, car manufacturers will not do that.
No, my new car is a hybrid, electric and petrol, but that has a very small petrol tank because of the fact that hopefully I'm generating quite a lot of charge as I drive, it can use the battery for some of the time.
Well, I have no problem with electric vehicles. I think they're a very attractive option. provided that you get the electricity from renewables. I'm not so much a fan if you get all the electricity from burning natural gas, because that produces CO2.
Yeah.
So even though you don't even though you don't produce CO2 at the point in your car, it may be produced upstream when you're actually generating the electricity. It does help with air quality. I don't doubt, no doubt at all. Going to a hybrid or a fully electric vehicle compared to diesel will improve air quality, and it reduces noise. But we can't forget that most of the time you're getting electricity from burning natural gas, so it's not entirely neutral. You're right, and a motor vehicle will need very specific kind of engineering solutions, so you don't dominate the vehicle by the store. But here's an interesting trick. One of my PhD students, a lovely lad called Will Forshaw, is working on a concept called swapping. And what that means, instead of going to a car and having a little sort of like a gun and feeding in the hydrogen, you just swap the tank. So in other words, the tank is in the car. When it's empty, you take it out and someone else puts it in a refueling station. And so you don't have to worry about ultra high pressures. You don't have to worry about all sorts of the fancy tricks of the trade for working with hydrogen. Someone else does that. And swapping could be a potential way. So in other words, you run low on the fuel, so you don't have to have a massive tank. You just have to have lots of refueling stations. So you're transferring the role of storage to somebody, almost like to somebody else. So someone else makes it, someone else puts it in these tanks, and it's the same way. You may have heard of swappable batteries.
Yes, I've seen this. I think in Japan or China they have. You see the cars driving up and they swap them over.
You can do it with cars. You can also do it with motorbikes and things like that. So in other words, it's someone else's responsibility to deal with the battery when it's flat or with a hydrogen tank when it's empty. Now this is quite a cutting edge, if I may put it that way. No manufacturer has yet committed to this technology. But because of the recent horrible events in the Middle East, people are now thinking that we really need to look inward, homegrown energy. And hydrogen can deliver that, because we do have a lot of natural renewable energy resource in the UK. And in fact, we're very lucky. Lots of wind, not so much sun, but enough. Lots of wave energy and tidal energy. So I think that hydrogen will play a big role in this sort of transition, not only to move away from carbon emitting fuels, but also to be working with homegrown, so we don't rely on imports. So,
Tim, you've been working with hydrogen for a long time now. Well, you were a child when you started.
I was,
of course. But so, how would you describe hydrogen in one word? And I know you're going to give me more than one word. I know.
No, I can give you a long word. Multifaceted.
Okay. Because of its use and and the way it can be used, or
particularly the way it can be used. I think it can turn its expertise, if I can put it into human terms, heating, power, chemicals, heavy industry. And there's a lot of it about. Hydrogen's not a rare commodity. Water's, I wouldn't say free, but water's the ultimate source for hydrogen. I'm not an expert on bio-inspired hydrogen, but you can get hydrogen from biological sources, but mainly we're thinking of using electricity to generate hydrogen from splitting water or heat. So I think that the idea that it's multifaceted, it's got lots of things going on, and that maybe have held its back a little. It's been held back a little bit because people want a simple answer, and there isn't one. There isn't a simple hydrogen will do this. Well, it can do this, it can do that, it can do that, and do the other. And I think that can mean that it's not clear in people's minds if they haven't been working in it for a long time, like I have. So it wasn't straightforward for me to understand the complexity of the system. I'm now a big fan, but I do understand that there are other options that are easy fixes. And a good example in the UK is reinvesting in the North Sea. But I think ultimately the price we will pay if we don't invest in hydrogen and nuclear, I'm a big fan of nuclear, will be the consequences of being vulnerable to energy supply, and secondly, in a longer term, having to deal with the dreadful potential consequences of climate change. I'll give an example, if I may. You may have heard of a thing called a heat pump, which is a way of using electricity to heat your house. And there was an article on one of the evening news broadcasts on Radio 4 where the measure of how a heat pump works is called its coefficient of performance. I'm afraid I can't avoid these technical terms. And it's a number bigger than 1. And it just measures how effective the heat pump is. So the number could be 2 or 3 or something like that. And I remember one of the broadcasters saying, "This is magic. You're creating energy out of thin air." No, you're not. That number is not efficiency. It's just the number that allows you to compare different heat pumps. My heat pump's better than your heat pump. It's a macho thing. And that drives me nuts because people then say, well, why do we even bother thinking of hydrogen for heating? Well, you're not going to have a heat pump in a flat. And we're where we are in Bath at the moment. There are quite a lot of flats and single occupancy build accommodation where you simply can't put a heat pump. And I've seen pictures of heat pumps; they're that big. So where are you going to put it?
If you've got a really big garden.
If you're in a detached house or in a semi, or you've got a bit of land around you, no problem. I don't have a problem with heat pumps, but it's what fits where you live. Now, down here, was it Snow Hill? You wouldn't be able to put heat pumps in those buildings and those flats because where would they go? So heat pumps might not all be this solution to everything for heating. And there are some people that will promote heat pumps because of this coefficient of performance, saying, well, it's like magic. And I remember the word on the radio, they're magic.
I think, as we've heard today, if people understand how hydrogen is generated or can be generated from renewables, then that is magic. And it is out of thin air because a lot of it could be from wind energy or from solar. So I think that's a lovely point for us to finish on. Hydrogen is as magical as a heat source pump and electricity. We need this mix, and it depends on where you are, your location, your topography, and everything that we've been talking about. So thank you for debunking some of the myths today around hydrogen and helping people to understand it a little more.
It's been a pleasure, Karen. Thank you.